Hey everyone, Morgan here. So we're going to be looking at a few pages of mathematical examples that deal with thermodynamics for AP Chemistry. We're starting on page number 10. Now, in the AP exam, Chem Olympiad, whatever test you might be taking, it is common practice for you to be provided the value of R. So I wouldn't worry about going out and memorizing that. That's just not necessary. Okay. So let's begin with this reaction. Zinc sulfide solid reacts with 3/2 mole O2 gas to give you zinc oxide solid and SO2 gas. And provided beneath each of these species is the value of the absolute entropy. And these have been measured in an old-fashioned unit that we don't use anymore, which is calories per mole degree. We do almost everything now in joules per mole degree. But I wanted you to see one example of this just in case you're looking at any of the older literature and wonder what's going on. For a long time, this calories per mole degree was actually referred to as an entropy unit, or an EU. So since entropy is a state function, we can calculate the entropy change for the overall reaction by doing products minus reactants. So delta S naught for the reaction equals, and we'll take these two values, 10.5 plus 59.4, both measured in EU, add them together, and then subtract reactants, which will be 13.8 plus, and now this is important, 3/2 times 49.0, also in entropy units. And when I go through and do that, the overall answer is negative 17.4 entropy units. The negative number is allowed because it doesn't represent an absolute entropy, it represents the entropy change for the overall reaction, and the entropy goes down. Okay, so now let's talk about some absolute entropies for a second. Zinc sulfide has a value of 13.8 and zinc oxide only 10.5. Why is that one bigger? More stuff. See, it turns out the zinc sulfide has more particles, more protons, more neutrons, more electrons, okay, which gives you more energy. Now, I can do that comparison and base that answer because they're both in the solid state. If they were in different states of matter, that would be a harder comparison to do. Why is the entropy of zinc sulfide smaller than O2? Easy. O2 is a gas, and zinc sulfide is a solid. So we're talking about gas versus solid. Why is the entropy of SO2 higher than O2? Again, more stuff. They're both in the same phase, so that's not coming into play here. Now, the overall change is a negative number. You got solid, solid, gas, gas. But what you have to realize is there's a 3/2 there. You have more moles of reactant than product. So that decrease in the number of moles causes the entropy to be negative. Okay, that's a good question for conceptual understanding. Now, number 2, gallium undergoes a solid-solid phase change. Okay, immediately what I'm cluing into is that delta G naught equals 0 for phase changes. It happens at 275.6 Kelvin, and the delta H for that is 2100 joules per mole. Let's calculate delta S. All right, so delta G equals delta H minus T delta S. I know that's equal to 0, so that means delta H equals T delta S, or that delta S is going to equal delta H over T. The delta H is 2100 joules. And now the delta S is 275.6 Kelvin. And when I go through and do the math there, it comes out to be 7.619. There was a decimal point on that. 4 sig figs is cool. Joules per Kelvin. And that is a very, very common, actually, I'm sorry, joules per mole on the delta H. So we can call that joules per K mole. And that is our very typical unit for entropy these days. Okay, always remember, phase change, delta G is going to equal 0. Now, number 3, I'm talking about the heat of formation of HBr. I've got the value. The entropy of formation, I have the value. Calculate the free energy change for this at 25 degrees Celsius. Okay, so that's pretty straightforward. Delta G naught equals delta H naught minus T delta S naught, which equals, now, negative 36.40 kilojoules per mole minus the product, it's 25 degrees, so that's 298K times, now this is 57.183 joules per mole K. Except this one is in kilojoules. So what I'm going to do is throw a little conversion factor in here. 1,000 joules per 1 kilojoule. Okay? Now, the Kelvin is going to cancel, and then the joules are going to cancel. They're both in kilojoules per mole. And when I run this through my calculator, I get negative 53.44 kilojoules per mole. All right. Okay. Nice, straightforward question. Because it's negative, I know that this reaction is going to be spontaneous. Okay. So, I have a kind of a brain teaser one here. H2S aqueous is going to dissociate. It's going to ionize into H plus aqueous and H minus aqueous. And it turns out that this reaction has a strange entropy change. Delta S naught equals. Now, the absolute entropy for H plus is 0. For HS minus, it's 61.1. For H2S, it is 122, all measured in joules per mole K. So when I do products minus reactants, I get 0 plus 61.1 minus 122, all in joules per mole K. And that comes out to equal negative 60.9 joules per mole K. Now that in itself is kind of odd. That's a negative. That typically would tell me that there's a decrease in entropy, but everything I know intuitively says this is an increase in entropy. They're all the same phase, aqueous, 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 but I have 1 mole turning into 2 moles. Why is this? Well, it turns out that there's a little, I'm going to call it problem with the definitions, the way we're talking about here. H plus is our reference point for absolute entropies. And in this case, that's a 0. Well, it's always a 0. But in this case, H plus is a product. So when I add those two together, I happen to be adding something to a 0. That means this is bigger than that. Okay? This does actually represent an increase in entropy. It's just that because we have defined or assigned the value for H plus to be 0, that this ends up happening. Okay, that's page 10. We are going to go on now and look at some more problems, starting on page number 11. Now, I have a phase change Br2 liquid to Br2 gas. At what temperature is this reaction going to be spontaneous? I've been given the delta H naught and the delta S naught. I have not been given the temperature. I've not been given the free energy. But I know what the free energy change is. At the normal boiling point, delta G naught is going to equal 0. Sorry, that looks terrible. 0. Which equals delta H naught minus T delta S naught, which means delta H naught equals T delta S naught, or T equals delta H naught over delta S naught. And I have 31.0 kilojoules per mole for the delta H. I have 93.0 joules per mole K. And now I need to get rid of the joules and get it to kilojoules. I can say 1,000 joules per kilojoule. And when I do that, the kilojoules cancel, the joules cancel, the mole cancels, and I'm left with Kelvin, which is good. And on my calculator, this comes out to be 333 Kelvin. So that represents the temperature at which bromine starts to boil. Okay, now switching gears. Different type of question. The equilibrium constant for the dissociation of acetic acid at 298 K is 1.75 times 10 to the negative fifth. Calculate the free energy change associated with it. Okay, delta G naught equals minus RT ln K, which equals negative. Now, if I go back one page, I can actually locate the different values of R depending upon what unit. And this is a very handy one, 8.31 times 10 to the negative third. So, 8.31 times 10 to the negative third kilojoules per mole K times 298 Kelvin, the Kelvins are going to cancel, times the natural logarithm of 1.75 times 10 to the negative fifth. And when I run that through my calculator, I get 27.1 kilojoules per mole. Now, that actually makes a lot of sense to me. I know that acetic acid is a weak acid. It does not completely dissociate. It dissociates less than 5%. It's really only a very, very partial dissociation. That's not a spontaneous reaction. And this is a positive delta G, which is what I would typically see for a non-spontaneous reaction. Cool. All right. Another different one here. I have this reaction, 1/2 H2 plus 1/2 Cl2 gives me HCl gas. At 25 degrees Celsius, delta G naught is given. What is the value of delta G naught for the process if the partial pressures of the gases are that? Okay, that's a question about changing between delta G naught and delta G. Delta G equals delta G naught plus RT ln Q, which is the reaction quotient, which equals, my delta G naught is negative 95.3 kilojoules per mole, plus the product 8.31 times 10 to the negative third kilojoules per mole K times 298 Kelvin, says at 25 degrees Celsius, times the ln of Q. Now Q in this case equals the pressure of the HCl divided by the pressure of the H2 to the 1/2, or you can call that the square root, times the pressure of the Cl2 to the 1/2. So upstairs I have 0.31, downstairs I have 3.5 to the 1/2 times 1.5 to the 1/2. Now, giving you a little bit of a hint or a clue here, on calculator work, I'd go backwards. I'd find Q, I'd take the natural log, then multiply them times that, and then add that on. And when you do, this equals negative 100 kilojoules per mole. All right. Good question. Number 8. So here we have a nice reaction, the dimerization of N2O4, two NO2s becomes N2O4. We have delta G naught. We'd like to know the value of the equilibrium constant Kp. All right. If delta G naught is equal to minus RT ln of K, I can say that the ln of K equals delta G naught over minus RT. And I can start plugging that in. Negative 4.77 kilojoules per mole. And then I have a negative sign there. R, 8.31 times 10 to the negative third kilojoules per mole Kelvin. I have a temperature of 298 Kelvin. Kilojoules, moles, and Kelvin all cancel. It's now unitless or dimensionless. That's good. That ends up equaling 1.926. That means the ln of Kp equals 1.926, or that the value for Kp is equal to E raised to the 1.926, and that equals about 6.86. That K is greater than 1. That means the products are favored, or in other words, the reaction is spontaneous. And the delta G naught is negative, which is good. That tells me the reaction is spontaneous. All right, so that's page 11. Let's go on now and look at page 12, the last page of the math problems here for the outline. So I'm talking about the same reaction here, which is 2 NO2 gas forms N2O4 gas. Now I want to calculate delta G naught for that based upon all of this. Now what I'm seeing is that I'm actually given the heats of formation for both species and the absolute entropies for both species. So the first thing I'm going to have to do, terrible handwriting there, sorry, is calculate delta H naught by doing products minus reactants. 9.16 minus 2 times 33.2, all measured as kilojoules per mole, and that equals negative 57.24 kilojoules per mole. Then for the entropy change, delta S naught, that equals 304.2 minus 2 times 239.9, but in this case, joules per mole K, and that equals negative 175.6 joules per mole K. And if I divide that by 1,000, that equals negative 0.1756 kilojoules per mole K. And that's good, so they're now both in the same unit. Delta G naught is going to equal delta H naught minus T delta S naught, which equals negative 57.24 kilojoules per mole minus 298 Kelvin. And even though it didn't specifically state it was 298 Kelvin, because this is delta H naught, we know it's standard conditions, which occurs at 298 Kelvin, times negative 0.1756 kilojoules per mole K. The K's cancel. They're both in kilojoules per mole, which is great, which equals negative 4.91 kilojoules per mole, which actually is in pretty nice agreement with what we saw on the last page, where it said the value was negative 4.77. So that's pretty close to it. Okay. Last question then here deals with the rusting of iron, which is something we know to be very spontaneous. We want to calculate delta S naught for this reaction. Now, interesting. I don't have all the values of the absolute entropies, so I just can't do a products minus reactant. I'm going to have to get this using delta G naught equals delta H naught minus T delta S naught, so that delta G naught can come over here, T delta S naught goes over there, T delta S naught equals delta H naught minus delta G naught, divide everything by T, and delta S naught equals delta H naught minus delta G naught divided by T. Okay, now I'm going to need the delta H and the delta G for both of these. I can get those products minus reactants, and it turns out these are both species that are in their natural states, which means their values are 0. Okay, so I'm really just concerned with the product here. Delta H naught equals 2 times negative 826, which equals negative 1652 kilojoules per mole. Delta H naught, sorry, I got that one's 2 delta G naught next. Also zeros for the reactants, so 2 times negative 743.6, and that equals negative 1487 kilojoules per mole. So now I can say delta S naught equals, I can plug these values in, negative 1652 minus negative 1487 divided by 298K, and these were both in kilojoules per mole, and that equals negative 0.5537 kilojoules per mole K, or I would more likely multiply by 1,000 and say 553.7 joules per mole K. Now, I can actually find the absolute entropy for the Fe2O3. The entropy change for that is negative 553.7, which equals products minus reactants. 2 times X, the unknown value, minus, parentheses here, 4 times whatever the value is for Fe. Now, since this has already been converted to joules per mole K, that's great. I can say 4 times 27 plus, then here 3 times 205, all in joules per mole K. So negative 553.7 equals 2x minus 723 when I've run that through my calculator. 2x equals 169.3, or x, which we'll call S naught for Fe2O3, equals 84.6 joules per mole Kelvin. Okay, folks, so that's a selection of pretty typical questions the AP exam might be asking or Chem Olympiad might be asking for your classic chemical thermodynamics chapter. All right, thank you for tuning in. This is Morgan signing off.